So thanks for coming. This session is a continuation of some points I brought up in the keynote. And in particular, I gave you something that was very close to the original specification of FRP, and then hinted at that there's a much more elegant specification. And I want to talk to you about this more elegant version for two reasons. One is because it's for the sake of FRP in itself, is to show you that it can just be described more simply and more elegantly, but much more importantly because it's an example of a general technique for specifying, for designing and specifying software libraries. and my 1:30, I think, the afternoon 2.5-hour workshop is going to go in much more explicitly with several more examples. So this is kind of a bridge between the two talks. So, super quickly, hopefully under a minute, a recap of the story so far. So functional reactive programming really is based on two key ideas. It's a domain-independent idea and a domain-specific idea. So the domain-independent one is to base the entire development of the API, its formal specification, its documentation, and its implementation on a precise specification in the form that I call denotational. So it has a precise simple denotation. And then the second principle is continuous time. And that was really kind of the key idea that was the germ that gave rise to functional reactive programming. Okay. So you can think of it in a sense as being a deterministic continuous concurrency. Now, I put concurrency in quotes because concurrency is usually an operational notion, and this is really denotational. There's no operation here. Okay. So, as I mentioned before, there have kind of been a lot of ideas floating around about what FRP is in the last few years, and most of them are really completely beside the point to me about what FRP was and to me still is. So FRP is not about graphs. Oh, thank you. Thanks. Yeah, if I do that again, please let me know again. Also, I want to say, please interrupt anytime with questions. If you have a dumb question, somebody else is even more confused about what you're confused about. So please don't be shy about that. I enjoy interactive presentations more than a monologue. So there are a bunch of kind of very operational notions, ideas about what some program is doing and updating what state and that kind of thing. None of that has anything to do with functional reactive programming. Those are all ideas about some ways that you might implement parts of functional reactive programming, and many of them are really unfortunate choices. So it's particularly harmful to get confused between these operational notions and what FRP is. Okay, so it's nothing to do with graphs, it's nothing to do with updates, propagation, that kind of thing. It certainly has nothing to do with streams in the sense of the common use of the word streams to mean discrete sequences. And when I say it's not about doing, I mean it's not about any operational model at all. Some implementations might be, but FRP itself is not. So the central data type in FRP is something I call the behavior, which you can think of as a time-varying value. That was what I wanted. It was originally came out of doing like 3D animation and 2D animation, other kinds of things. And I realized that if I wanted to build up these things that vary over time, these things that are not static, you can think of dynamic is another way to say it. I want to do it in a compositional way, then I want to, at every level, from the very finest, like a Boolean or a number, up to the largest thing, an entire three-dimensional interactive scene, I wanted to build up compositionally every bit of it as time-varying values, as first-class values. Okay? So I have this mental model. It's not just a mental model, it's a formal model. The meaning of a behavior is a function from time to alpha. It's critically important that time is reals and not something discrete like integers. Okay. And then I mentioned that from this one choice here, most of FRP can follow. Okay? So almost everything that's important is in this one small statement right here. The meaning of a behavior is a function from time to alpha. Okay. And so the purpose of this short talk is to show you how that works. So this was a description of more or less the original API I showed yesterday. I won't go into it in detail, just a little reminder. So this is the precise meaning of each of the constructs in the API. So that's the idea. We define an API, and the API is going to be typed That is back here. So the API is going to be typed. And then we want to define meaning compositionally, which means the meaning of, well, the meaning of, say, lift 2 of its 3 arguments is going to be a function of the meanings of those arguments. Okay, that's what we mean by compositional, sort of recursively defined on the structure of the API. And so here's a precise definition. You can see it's pretty simple. So the meaning of behaviors is going to be a function, and I'm writing those functions as lambda expressions over here. So, and then we can just do a little bit of refactoring, use some idioms to make these right-hand sides just a little prettier. Okay, not quite so low level in terms of explicit lambda abstractions. Instead, we define them in terms of higher level building blocks like composition and constant identity, that kind of thing. Now, to me, that makes it sort of higher level. I'm no longer talking about the mechanics of what happened when given a time. This is how you compute. Now we're talking about composing functions directly. And then we have this secondary type of events. Events punctuate behaviors. So if you think of continuous, so behaviors are anything that varies with time. If you're interested in a value, even if it doesn't change continuously, so I might slip and accidentally say continuous functions, but I really mean functions of continuous time. So the functions can have discontinuities in them, right? But what's important is that they're defined at every moment in the temporal continuum. Okay, and what I mean by continuum or continuous is that if you take any 2 distinct times, there are times in between them. Okay, so there's no kind of finite granularity. There's no finite resolution there. So a behavior is anything that has a value over time. So for instance, waving this around is a behavior. So it's a function from time to a spatial location and maybe an orientation, that kind of thing. If I advance the slide, I go back or forward, I'm going to click a button, that's an event. So it's a discrete moment in time something happens. So it doesn't carry a value through time. It's that at times, discrete times, we have values show up. And then reactivity comes from the interplay between these two. So I don't know if there are any questions about that. Okay, so that's the story so far. That was a little more than a minute, I'm afraid. 10:40, great. So now I want to show you a more elegant way to approach API design in this context of functional reactive programming. So many of the operations that were in the original API look like more general operations. So there was a mapping kind of a thing. If I had a behavior and I had a function, then I could map that function over the behavior. So it gets applied at every moment in time. Okay, uncountably many moments, the whole continuum. Or if I have 2 behaviors, and I have a function of 2 arguments, I can just imagine those 2 behaviors in parallel, like continuously. That's what I mean by continuous concurrency, so to speak. And then that function of 2 arguments gets applied. So at every moment in time, that function of 2 arguments gets applied to the values of the behaviors. Okay, and that happens across time. So that pattern looks like applicative. That's the kind of thing that applicative does. And then there was a thing I called lift 0, the constant behavior. That also comes from applicative. There's something called pure there. It's also the case in particular that if I have 2 behaviors and I have some kind of monoid, a monoid is just it's this algebraic pattern where I have an identity operation and I have an associative identity value in an associative operation. And identity is the identity for that associative operation. So as one kind of special case, if I have a monoidal value and it's varying over time, if I have 2 of them, then I can combine them, and it just means apply the monoidal combination. Or this the empty, which also comes from monoid, is the constant empty. Okay? And similarly, events. Now, so events happen discretely. So at every moment, if I have an event and I have a function, then whenever that event occurs, I can apply the function to the value that the event yields. That gives me a new event. And similarly, there's another monoidal operation. Did something happen with the sound, or is that my imagination? Are you okay? Okay, great. So if I can combine 2 events in such a way that the new event occurs whenever either of the 2 occur. Okay? And it also has an identity, and it's associative. Okay. Why does this matter? Okay. It may matter just for aesthetics, but it also has quite practical implications. It means that there's a lot less that we need to learn because it can leverage what you've already learned. Once you learn these abstractions, there's a huge payoff because they come up over and over, and that's why we have them because they came up over and over in the last several hundred years in mathematics. And then, as I'll show you, we get specifications for free. And to me, that's a huge payoff, and they're law-abiding necessarily. So the first observation is to notice that the meaning, so in this example, the meaning of a behavior is a function from time. So behavior of A, its meaning is function from time to A. So A is a type parameter here. Now, if we look at the meaning instead of the behavior, so behavior is this kind of new mysterious thing that we're in the process of designing. Once we know its meaning, then we can ask questions about it instead, and then we can transfer what we understand about its meaning back to the type we're defining. So this may look funny. It even looks funny to me, and I've been programming in Haskell for a long time. But if a function from, let's say, from Z to A, so the domain is Z, the range is A. So function from Z to A, if you take off the A and just have function from Z, right, it's missing a type. So in other words, it's a parameterized type. So function from Z is the kind of thing that might be a functor, applicative, monad, foldable, traversable. Okay? And so we can ask the question, is function from Z a functor? And the answer is yes. And I'll show you in another slide or two what the instances are. And similarly, that one, it's also an applicative. And then, I keep hitting the wrong button here, back, that way, okay. And then similarly, we can ask the question about is it a monoid? Function from Z to A. So here, monoid just wants an actual type, not a parameterized type, not a type function. So is this guy a monoid? Well, yes, it is, if A is a monoid. Is this guy a number? Functions from Z to A number? And the answer is yes, if A is a number. Now, that may surprise you, but it's quite useful. So this information, which we didn't invent, okay, I want to point out. So we're inventing the idea of behavior and we invent the idea of events. But we didn't invent the idea of notion, of functions. That notion has been around for quite a long time, and there's a lot we know about it. Why? Because it's so useful. It's been applied in so many places, and there's been a lot of exploration. So this, I did it again? Okay. Yeah, there's something that's cross-wired in my brain about these buttons here. There we go. Okay, so we didn't have to invent. We got this information for free. And what I mean by for free is the community provided it for us. They paid for it. All right, so now, what do we do with this information? And what I'm saying up here is that what we know about functions, in other words, the denotation, the semantics, will tell us that it translates directly into information about the thing that we're in the process of inventing, about behaviors. And now I don't think I did that, but I suppose maybe I did. Okay, I'll just be careful how long I hold the buttons. Okay, so what we're trying to describe, or what's sort of coming out of this design process, follows from the semantics in what I'm going to call precise analogy, and then I'll make that notion more precise. There we go. And something called homomorphisms, and this is hopefully the only scary word I'll use in this talk. And a homomorphism is something that's come up over and over in algebra. It's turned out to be very powerful notion. And I'm going to show you exactly what it means. It means that it's kind of structure preserving. That's what homomorphism means. It means the same shape. That's what the word means. And there are several examples of it, and this is the one for monoid. So monoid has two operations. It has the empty and it has the combine. And so a function h is a monoid homomorphism, if and only if these two properties hold. And one of them says that h maps the empty value to the empty value, and h maps the combination to the combination of the h's. So h of the combination is the combination of the h's. Okay? That's exactly what it means for h to be a monoid homomorphism. Now, here are some examples. If you have two lists, if you have a list and you want to be able to take the length of it, okay, so we've got lists and we have a function length. Now, there's an interesting property about the length function, which is that if you take the length of two lists, okay, so you've got two lists, you take each of their length and you add them up, you get the same result as if you had concatenated the lists and then taken the length. Okay. So if we think so the length function maps lists to integers, and integers form a monoid, well, in more than one way. One of those ways is addition. So, and lists are a monoid, where the combining operation is append. So another way to say that the length of an append is the sum of the lengths is to say that the length of the monoid combination is the monoid combination of the lengths. Okay? It's two different monoid operations, but it's the same abstraction. And that's what's going to happen over and over. That's the pattern here. Now, the technical thing, which is, this is a Haskell thing, not a math thing, that we only have one kind of class instance per type. We can't have two different integer monoids. So there's just a little new type wrapper called sum that says there's actually no representation at runtime. It just says statically in the type system we know which of the monoids we're talking about. So another example is that the log of a product is the sum of the logs. Okay, so a logarithm is the property. That's another homomorphism property. And I've given you two examples of this homomorphism property, but there's also this one, which is the length of the empty list is 0, okay, and the log of 1 is 0. Okay, so those are examples of monoid homomorphisms. But every algebraic abstraction, or in Haskell we call them type classes, every one of these abstractions come with its own homomorphism property. Okay? So for functor, the operation that functor gives you is fmap. And to say something's a functor homomorphism, or I'll just say a functor morphism sometimes, is that H, so H is a functor morphism if and only if H of fmap is fmap of H. Okay? So I can take fmap and apply it before or after H, and I get exactly the same result. So that's what it means to be a functor homomorphism. So you can see what's happening is H is getting kind of pushed down into the internal structure one step at a time. And the structure kind of comes from the outside. So another way to say it is it's like a distributive property. And for applicative, we have two operations. So we have two homomorphism properties. I want to say H of pure of A is pure of A. So I've distributed the H into all the internal structure of which there is none. That's why the H disappeared here. Okay. Here, fmap, right, has one argument that's of the same structure. Fmap of a function over a list gives you a list. So it's got like one list. Or fmap over a behavior is a behavior. Aaron?
The H in this context is a function that still respects its homomorphism, right?
No, H, okay, so the question is, what I'm saying is, you give me any H that has the right type. Okay, it's got to be a function. Okay, and I'm telling you what it means to be a homomorphism or not. If this property holds for all f and x's, then H is a homomorphism. Okay, thanks. And so applicative has two operations, so it has two laws. One says that H goes into all, none, right, of the kind of sub-objects. Whereas the applicative combining operation, this takes like, if this were lists, it would be a list of function and a list of arguments, okay, or a tree of function, a tree of arguments, or a behavior of functions and a behavior of arguments, or an event of functions and an event of arguments, okay? So this says that what it means to be an applicative morphism is that H distributes over the applicative structure. So the combination, so H of the combination is the combination of the H's. And then the monad homomorphism law, well, there's one for return, which is the same as pure, because they're the same thing. And then the monad homomorphism properties, it's a little more complicated because of just because of the types in here. If you look at the types, nothing but this law would type check. I mean, it's sort of, you could figure out what these laws are going to have to be just by looking at the types. So it's very regular. There's another form if you like join instead of bind, which I do. You can also figure out what that has to be from the types. Okay, so 1052. All righty, so now I want to give you this. This is the key principle, okay, of what I call denotational design, which is our specification. So remember, designing a library, and the most important thing in the library is what do the types mean? Okay, that's the most important statement to make. What does the type mean? In other words, what's a simple, precise mathematical model? And then the next step is for each of the primitives in the API, what does it mean in terms of the meaning of the type? Okay, some story about that. And so originally I came up with, well, here's the API, and I thought about each one individually, and I thought, well, here, this is the meaning of the operation. And I want to say is you can throw all of that out. For every operation that comes from a standard abstraction, I don't need to specify it because there's one general way to specify them, and that's to say that the meaning function is a homomorphism. Okay? For every type class that my type inhabits, so behavior has, functor, applicative, it can have monad, it's got numeric stuff, and it's got monoid. For every one of those, I'm saying the meaning function is a homomorphism for that class. Okay? That's the only specification we need. And that, to me, is like the ideal specification, because when I say to you, think of a behavior as a function from time, this is what I mean. If this is ever not true, then I've hurt you. I've told you something, I've given you an understanding that you can injure yourself with if you believe it, okay? But if these homomorphism properties are true, it's saying exactly that when I tell you, think of it as a function of time, and if you use the interface that's common between functions of time and my type, they behave equivalently. So when I said think of it like, it behaves like, a precise way of saying that is it's a homomorphism. Okay. So if ever this principle fails, I'm doing a design, and I'm saying, oh, I see what its meaning is, and it's applicative, and I see what, and then I want to say my thing's an applicative, and the homomorphism doesn't hold, that's a design bug. That means I'm unclear. I have to figure out a better model. And getting alerted to that very early, super helpful, because it steers me toward an elegant, predictable, well-founded, simple, precise design. Okay. So this is what it means. So I'm saying the specification is that mu is a homomorphism. So this is more than one statement. It's a functor homomorphism, it's an applicative morphism, it's a monad morphism, it's a monoid morphism, it's a num morphism, and so on. So for example, I'm just repeating what I said before, but more specifically. So now we're talking about mu being a morphism. We will go that way. Okay? So I just mean the meaning of fmap is fmap of the meanings. All I did was take the general definition of morphism where I said H, now I'm saying it specifically for meanings. So this is the specification. Now, how does that play out? I remarked yesterday that the original denotation I gave, the original specification I gave for FRP is exactly equivalent to this. I didn't know it at the time. So I thought about it, what should it mean? I came up with these definitions. What I didn't know was those definitions fall out for free from this general pattern. So it helps to know, and this is exactly how I discovered this principle, is in the intervening time between when I invented FRP and when I wrote a kind of modern version of it, a paper in 2009, I gained quite a lot of familiarity with the standard type classes and the instances of those type classes for common types, pairs, sums, functions, that sort of thing. Okay, so I know that this is the monoid instance for functions. The empty function it's the function from z to the empty value. Okay? So these empties on the left and right are different empties. The one on the left is for functions, is for function from z to a. The one on the right is for a. Okay? So the empty function is the function that always gives you empty. The monoidal combination of two functions is the function you give it z, and you apply f and g both to z and combine them. Okay? So if you see on the right-hand side, we're using epsilon here. We're using empty and combine, and on the right, so the right-hand side, we're using empty and combine for a. The left-hand side, we're defining empty and combine for z to a. So this is a very common pattern, you'll see. And then what does it mean to map a function over another function? Does that make any sense at all? To map a function over a function? Well, if you write out the types, you'll see there can only be one thing, and it's composition. So if you look in the standard library, poke around the source code, Haskell's Prelude, you'll see this definition. And then there's also a definition for applicative. If I have two functions, okay, well, let me start simply. Pure A Okay, what function is it going to be from z to a? Well, there's really only one thing it can be, which is the constant function. And similarly, if I have a function from z to a function from a to b, and if I have a function from z to a, okay, I can combine those into a function from z to b. And as you play with the types, there's only one thing that's going to type check, and it's the right thing. And this is what it is. Okay? So I don't know if you've heard of them before, but a long time ago in the 40s, I think it was Haskell Curry developed something called combinatorial algebra. Is that what he called it? It was another approach to functional programming. So Church came up with lambda calculus, and some other folks, including Haskell Curry, came up with a kind of a algebraic building blocky way of defining functions. And one of them was called S, and that's exactly this guy. And one was called K, and that's exactly that guy. Okay. So this is kind of lovely that it occurs again. So now we can put these two pieces together. If we know, so we know what we want. The meaning of pure is pure. That's the homomorphism property. And we know what pure is for functions. Okay? So this is behaviors, this is functions. And we know what this means for functions. It means lambda TA. So we've just deduced that the meaning of pure A has to be lambda TA. Similarly, this is the other applicative operation. So this is the homomorphism property, which is our specification. But we know what this is because we know what the applicative instance for functions is. It's this. Okay? And this is exactly what the denotation for the applicative instance must be for behaviors. So I didn't have to invent it, and that's very important. It's very important not to invent things because I might be deluded, I might have some kind of special focus, I might have a personal bias. Okay? But if mathematics, if the universe is kind of inevitably is telling me what it has to be, then I know that's going to be a solid design. Okay. And then it turns out, and it looks like I didn't balance my time very well here, but we get laws for free. Okay? And what I mean is that if we have the homomorphism properties over here, and if equality on my data type that I'm inventing is semantic, okay, by which I mean things are equal if and only if their meanings are equal. Okay? If those two properties hold, then the laws must hold. Okay? And there's a simple proof. It's just a structural proof. You just kind of push. So what I want to prove is, this is, for instance, I'm trying to prove this identity property, and I want to prove that, and semantics is equal, so I mean the meaning of the left is the meaning of the right. If I just use the homomorphism properties to push the meanings into the structure, because that's what they're about, it turns out that I can then use the law for the meaning. Okay? So the fact that the laws hold for my meanings, combined with I'm using a homomorphic meaning function, and with semantic equality, those three properties, and they're all really important properties in themselves, they imply that my laws have to hold. Okay, so that's also a very good sign. Okay, and then there's a story for events, which I'll skip over here. All right, so here's the conclusion. As I mentioned, FRP is really about two things. Having a precise, simple denotation, which I encourage you to do every time you do library design, and then, in particular, continuous time as the germ idea. And then what I've talked about briefly here is this idea of using semantic homomorphisms as a specification. That just means that the meaning function distributes over the kind of the API structure of these abstractions. So. And you get very nice properties. The semantics invents the API, or it suggests one for me. Okay? It tells me exactly what the API has to mean, so I don't get to choose that, which is a good thing. And the laws hold for free. They hold inevitably. You can go prove them if you like for fun, but they'll always hold. And then I want to make this sort of strong claim that this methodology guarantees you will not have abstraction leaks if we apply it successfully. But it's also very helpful if you apply it unsuccessfully. If I apply it and find out that the homomorphism properties don't hold, then it means I have an abstraction leak and I want to redesign. Okay, so that's it. Oh, and then my longer workshop this afternoon is going to go into several more examples at a more leisurely pace. So if this was a bit fast for you, but you're intrigued, I invite you back. Go at a slower pace and have much more time for interaction. Okay. Thank you.